Whenever I teach acids and bases to undergraduate students, it's easy for me to get caught up in the jargon. Ka, acidity constant. Okay, pKa, why do you need that? And then conjugate acids and conjugate bases, Lewis acids and Lewis bases. What's going on? What's really important about this stuff, and why do we need to learn it? How do we ever apply it in chemistry and in science in general? In this video, I'd like to explain what is important and what you really have to know about acids and bases, at least to pass in introductory organic chemistry. So firstly, we need to be able to quantitate the number of protons in solution. And to do that, we need these special terms, Ka and pKa. Ka is nothing special. It's just an equilibrium constant, gives you the concentration of acid in solution. For organic molecules, Ka's are likely to be small. For acetic acid, on the order of 1.8 times 10 to the minus 5 moles. That's a small number. But if we get into the really bad acids, methane is one of the worst I can think of. Ka is 10 to the minus 60. Now, I can't picture 10 to the minus 60. That's such a very, very small number. And we need some way of keeping it on the same scale. And we do that, of course, with logs. So we take the log of the Ka. Okay, so if you take logs of Ka's, this contracts the scale. When you start talking about differences in 10, for the concentration difference, every one difference in log Ka. But then if you're taking logs of small numbers like 10 to the minus 5, everything will be negative. And that's for most organic compounds. So let's flip it again and say minus the log, pKa. And then the numbers turn out to be positive. So how does that work out? Well, a molecule with a low Ka will have a large pKa, positive, and that will be a poor acid. A molecule that has a big Ka, generates a lot of protons in solution, will have a small pKa, even a negative pKa in some cases, and it will be a strong acid. So then we can compare acid strength in terms of a strong acid, low pKa, and a weak acid or even a mild base, a higher pKa. So for instance, acetic acid has a pKa of about 4.7 and methanoic acid has a pKa of about 3.8. There's a 1 pKa difference between them. Methanoic acid, formic acid, is about 10 times stronger than acetic acid. Let's suppose we take a proton and we add it to water, and we form a hydroxonium ion. That is the conjugate acid of water. That's the thing that we get from water when we protonate it that acts as an acid. Let's say we take water and remove a proton, and then we get OH minus. That's the conjugate base of water. And there'll be different equilibrium constants for both these processes. Similarly, for ammonia, NH3, the conjugate acid is NH4 plus, the conjugate base is NH2 minus. Okay, so we're over the first hurdle. We know how to quantitate the concentration of acids in solution, and we're doing it in terms of an equilibrium constant. So it doesn't matter how much acid you've got. What matters is the concentration of the acid. It doesn't matter if you've got 100 mils or a beaker of 1 liter. It's still going to be the same concentration of protons for a certain pKa acid. So we know where Ka comes from, pKa, and now we know about conjugate acids and conjugate bases too. Having decided that a certain acid will give you a certain quantity of protons in solution, we can use these parameters to predict which molecule may or may not protonate another one. Does a proton transfer occur in a particular situation is important for predicting how the reaction will proceed. Let's say we mix nitric acid and sulfuric acid. Well, it turns out actually that sulfuric acid has the lower pKa. It's the stronger acid. So sulfuric acid protonates nitric acid in solution. That means actually that nitric acid is the base under these conditions. Everything is relative in the world of pKa's. Let's say we don't know the pKa of a particular molecule. We don't know the vital parameter for predicting how many protons we will generate. How can we look at the molecular structure and predict how good an acid it will be? Just like Gandalf the Wizard, I've re-emerged as Kevin the White. Before we move on, what about these terms Lewis acid and Lewis base? In sophomore organic chemistry, introductory organic chemistry, they're not really very important. Usually there's only one question or two questions on the exam that could relate to these. So a Lewis acid is anything that can accept a lone pair. It could be a proton, but it doesn't have to be. It could be something else. And a Lewis base is anything that can donate a lone pair. The classic example is adding ammonia to something like BH3, borane. The ammonia nitrogen donates a pair of electrons to the boron, which is only 6 electron species, and therefore forms an adduct of an ammonium and a borate anion. That's a Lewis acid, Lewis base adduct. Okay, pKa is a bulk phenomenon. You dissolve an acid in, for instance, water, and you observe the concentration of protons that are formed. And pKa enables you to predict this. But pKa doesn't say anything about how the protons are formed. That's governed by the molecular structure. To understand how the protons are formed, you look at the molecule and ask, does it have any ionizable protons? If it does, the anion is usually stabilized in some way. Now, for a weak acid like methanol, the anion is stabilized because the negative charge is on oxygen. Oxygen is electronegative. Phenol is an aromatic ring with an OH on it. If that dissociates, then the oxygen is stabilized by resonance, and that gives you a higher pKa, and that makes phenol a stronger acid than methanol. Acid-base theory also tells us something about where molecules will protonate, and this is very important for determining reaction mechanism. One of the classic examples is amides. Let's take acetamide. Acetamide plus acid, if it were to protonate on the nitrogen, no resonance will be possible. But if acetamide protonates on the oxygen, the lone pair from the nitrogen can delocalize into the oxygen atom. In other words, protonated acetamide, when protonated on the oxygen, is stabilized by resonance. That makes the oxygen actually a stronger base than the nitrogen. Okay, now what's the big picture? Why is this so important? Well, in introductory organic chemistry, usually later in the semester or later in the second semester, you will learn all about the carbonyl group. And one of the problems of a lot of textbooks on carbonyl chemistry is they mix mechanisms in acid and basic conditions. I wish they didn't do that, because every reaction of a carbonyl compound under acidic or some under neutral conditions involves protonation of the carbonyl first, and then addition, say, of a neutral nucleophile. But under basic conditions, if we can have an anionic nucleophile that wouldn't be protonated because it's under basic conditions, it adds directly to the carbonyl without protonation. You can't have protonation in basic conditions. Those two avenues to draw a reaction mechanism are related to acidity. If you have to determine the mechanism of a reaction of a carbonyl, look first at what is the pH of the reaction. Is it neutral or acidic? Is the anion neutral, or is it basic? And this makes all the difference. I hope that helps with acid-base chemistry. Thank you very much for listening. Take care. Bye-bye.